In this module, we will discuss electromechanical actuators. In the previous module, we introduced electromechanical systems, and in particular looked at sensors as an example of electromechanical systems. In this module, we will look specifically at electromechanical actuators. We will first look at solenoids, then we will look at DC motors in quite a bit of detail, generating their mathematical models, discussing how they're controlled, etc. And then we will close with a brief discussion of a few types of AC motors, but we will talk mostly at a conceptual level and won't get too much into the mathematical details. Many electromagnetic actuators employ electromagnetic induction. In this sense, the actuator converts electricity into a force or a torque. Examples include solenoids, speakers, and electric motors. The basis for this is a physical law called Lorenz's law, which says that a current-carrying conductor in a magnetic field generates a force. And this works on the same sorts of principles we discussed previously with sensors. Current flowing through a conductor generates a magnetic field, and then that magnetic field can interact with the external magnetic field to create a force. One example of an electromagnetic actuator that's very common is the solenoid. And the way that it works is it has a coil of wire, and the current flowing through that coil generates a magnetic field. And so when this switch is closed, current flows through the coil and it generates a magnetic field represented by these dashed lines. This magnetic field then imparts a force on this iron core, causing it to move, in this example, downward. When the switch is released, causing current to stop flowing through the coil, the magnetic field disappears and the iron core is returned to its original position by a spring. This sort of actuator has many applications. It's used as a valve or a switch. For example, your door lock switch, you press a button and the door locks. That's most likely a solenoid actuator. Another example is a car starter. This is also the same principle on which a speaker works on, except with a speaker you have sort of a cone attached to the core, and by varying the current through the coil, the force acting on the core, which is attached to a cone, its movement changes, generating different amounts of noise, sound. Another very important example of an electromagnetic actuator is a DC motor. And again, it works on the basis of Lorenz's law, where current moving through a conductor in a magnetic field induces a force. And this is the mathematical representation of Lorenz's law. The force is equal to the cross product of the current and the magnetic field. Over here we have a simplified diagram of a DC motor, and you can get a sense of how it works. So there's a circuit that's attached to a voltage source, a battery, or whatever. It's a DC motor, it's a DC source. DC stands for direct current, so the current always flows sort of in the same direction with a constant voltage. And so the current flows through this circuit, and you can imagine, that's the direction of the current. There's a magnet surrounding this circuit, generating a magnetic field whose direction is indicated by these light blue lines. So this is the direction of I, that's the direction of B. This cross product you can determine the direction of the result using the right-hand rule. So you cross the current vector with the magnetic field vector, and the force will push down. So on this little segment of wire, there'll be a force pushing it down. As the current flows around the circuit, on this side of the circuit, the current is now flowing the opposite direction. So when you do the cross product, when you do the right-hand rule, the resulting force will push in the opposite direction, and it will be up. And so you have this coil where one side is being pushed down and the other side is being pulled up, and it'll cause it to rotate. And that's the basic notion of how a DC motor works. There's a couple challenges that arise, however. You can imagine that as these forces cause the rotor, causes this coil to flip. When it flips to the other side, this side of the coil is now over here, and so you can see that the direction of the current will be opposite the direction that it originally was. And that will cause the forces to switch, and you could imagine that it would want to make the coil flip back in the opposite direction. And so you wouldn't end up with a motor that's continuously spinning. In essence, the alternation of the forces would cause the coil in the middle to reach some equilibrium where it's basically just standing still. And so the way that this is addressed is that when the coil flips over, we need to switch the direction that the current is flowing through the coil. And that's accomplished with what we call a commutator right here. So this is sort of broken half rings such that when the motor coil flips, this side is no longer attached to this side of the battery. Rather, it's attached to the negative side of the battery, and that in essence causes the electricity to switch directions, keeping the force and the resulting torque always in the same direction. So it's pushing down. When it flips over, the current switches direction, so it continues to push down. That will keep the motor spinning in the same direction. Another challenge with a DC motor is that in essence we're trying to get electricity to this thing that's spinning. So you could imagine if we had a sort of a solid physical connection, you could imagine the wires getting tangled up as it spins, as it continues to spin. And so the way that this is addressed is that DC motors include brushes. So this electrical connection here between the battery and the commutator, there are little wire brushes that slide along the commutator such that you're able to get the electrical connection, but you're still able to have the coil rotate. So that's very quickly the basic idea of how a DC motor works. The parts that make up the motor include the stator, which is the stationary part of the motor. The most important part of that is the magnet, as shown here. So this magnet is a permanent magnet, and it doesn't move, it's fixed. The part in the middle that's spinning, this spinning coil, is called the rotor. It's the rotating part. It's also called the armature. And then this part that causes the current to switch direction, these half rings, is called the commutator, and it connects to the current source through little brushes. Here's a little animation to try and further illustrate what we were showing in the previous slide. So as it spins, the current is flowing in one direction. The magnetic field is constant in its direction. This light blue represents the commutator. So as it spins around, there's a break in the commutation, and it stops the current from flowing, and then when it reconnects, the current is flowing in the opposite direction. When there's this break, there's no current flowing through the rotor, and so there's no force being generated. But the rotor continues to rotate because of sort of the momentum, the inertia of the rotor. And so it'll continue to rotate in the direction it was going until the commutator reconnects on the other side. So in the previous example, we had a very simple sort of schematic or example of a DC motor, just to try and give you a sense of how it works, of the underlying physical principles that make the DC motor work. This example, this picture, shows a little bit more realistic version of a DC motor, how one might actually look in practice. So in the previous example, we basically only had two magnets, a magnet with a north pole pointing towards the center of the motor, and a magnet with its south pole pointing towards the middle of the motor. This DC motor is what we call a four-pole motor because it has four magnets. It has two magnets with their north pole pointing towards the middle and two magnets with their south pole pointing towards the middle. And these four magnets interact to create these magnetic fields shown by these dashed lines. In addition, in the previous example, we had a single coil, a single length of wire. In reality, a real motor, a real DC motor, is going to have multiple coil windings, and you can see that here, where the dot shows that the current is coming sort of out of the page. The X is the current sort of going into the page, where each dot will be matched up with an X on the other side. And the examples where there's no current flowing at all, you can imagine that's where the commutator is in its break, so no current is flowing through the coil at all. The reason we use multiple coils and multiple magnetic pairs is to ensure that the current carrying wire is near a magnet for a higher proportion of time. And this will generate more torque, the wire being close to the magnet, there being multiple coils. So there's higher torque, and it also generates less cogging, which means the motor will move more smoothly. It won't be jerky. It'll flow smoothly. Here's a picture of a representative motor, and you can see here is the rotor where there's multiple sort of windings. And over here is the commutator, and you can see again that there's breaks in between each of the sort of wires, so that as it spins and reconnects, the current will change the direction that it's flowing. Real motors also wrap the armature around an iron core, and the reason that it does that is so that the magnetic field doesn't have to cross a large air gap. Crossing a large air gap weakens the magnetic field. So in this case, you have the coils wrapped around an iron core, which helps to keep the field stronger. And that's also shown here, where the coils are wrapped around this iron core. Here's another picture of a realistic and actual DC motor. And in general, there's two approaches to control the DC motor. We're in essence trying to control the torque, or the force acting on the rotor, which will affect how fast the motor spins, how much torque the motor generates. Looking at Lorentz's law, the strength of the force is affected by basically two things: the amount of current and the strength of the magnetic field. And so those are basically our two options for controlling the motor, either affecting current or affecting the magnetic field. Controlling the motor by affecting current is called armature control. So we change the torque by changing the current in the armature. The alternative, affecting the magnetic field, is called field control. And so in order to do that, the magnetic field needs to be generated by an electromagnet. If we had a permanent magnet, you can't change the strength of the magnetic field. So we need an electromagnet, and that's what's shown here. So here's the rotor with its coils, its armature, and then here these coils represent the magnetic field. So by changing the current through this coil, we can affect the strength of the magnetic field. So in these approaches and in this picture, we have what's called a separately excited motor. The circuit for the armature is separate from the circuit for the field, and so we can control them independently. And in fact, we can actually combine armature control and field control in the same motor. Cheaper versions of a motor may not have separate circuits for the field and the armature. They may have the armature circuit and the field circuit in series, or they may have them in parallel. And so in that sense, we can't control the two independently. That makes speed control and torque control of a DC motor more difficult and less precise. So that sort of approach may be sufficient for a cheaper motor, for example a starter motor, but it's not something you would want to do for a more expensive motor or a more important motor, like for example a traction motor used for driving a vehicle. So far we've examined the underlying physical principles of how a DC motor works. Now we would like to actually generate a mathematical model of the DC motor, either a dynamic model or a static model. We're going to do that first for an armature-controlled DC motor. So here is a schematic of such a motor where the current through the armature is affected with this voltage source, and the magnetic field is fixed either with a permanent magnet or an electromagnet with a fixed voltage and current. In order to generate this mathematical model, we need to sort of make some simplifying assumptions. And one simplification that we do is to employ a lumped parameter model. So this circuit represents the armature or the rotor of the motor. And as you recall, physically it's a coil of many windings of wire. And so there wasn't literally a resistor and an inductor within the motor, but we can take that long length of wire and we can capture its resistance properties in a single parameter RA and a single inductance parameter LA. We can similarly do the same sort of thing with the mechanical portion of the motor. So the spinning rotor has some inertia, some rotational inertia, and the spinning of the rotor, the rubbing of the brushes, things like that, cause friction. And so we lump all of the inertia of the rotor in a single parameter J, and all of the friction of the motor in a single parameter B, which we'll think of as a damping coefficient, a viscous friction coefficient. Thinking back again to how the motor works, from Lorentz's law we know that the force generated on the rotor is a function of the current through the armature and the strength of the magnetic field B. Also thinking of how a force acting at a distance, or a force with a moment arm, generates a torque, we can come up with an equation for the torque being generated by the motor or applied to the rotor, where this constant K basically is based on the geometry of the motor, the number of coils, the position of the coils relative to the magnetic field. And since we're dealing with an armature controlled motor, the magnetic field is also constant. And so we can lump these two constants K1 and B into a single constant K, which we call the motor torque constant. And so the torque generated by the motor is proportional to the current through the armature with some proportionality constant K, which depends on the geometry and the strength of the magnetic field. From Faraday's law, we also generate this relationship for what we call the back EMF. And so if you think back to our discussion of sensors, you may remember that a conductor moving through a magnetic field can have an EMF induced, or can have current induced in the conductor. And so that's what we have here. The fact that this rotor, this piece of wire, is moving through a magnetic field induces an EMF or a voltage in it that's proportional to how fast the conductor is moving. So it's proportional to how fast the rotor is spinning. And we call it a back EMF because in general, most of the time, the EMF that's induced is in the opposite direction of the externally applied voltage. And this K sub B is called the back EMF constant. If you're in a situation where the units of the two Ks, the K and the K sub B, are consistent, the motor torque constant and the back EMF constant are equal. That's a little unintuitive, but it's sort of an interesting result. In order to generate a mathematical model of an armature-controlled DC motor, we'll need to use those relationships on the previous slide from Lorentz's law and Faraday's law, but we also need to be able to model the electrical aspects of the motor and the mechanical aspects of the motor. And so in order to do that, we can use the same sorts of approaches we used previously in the semester when we were modeling purely mechanical systems and purely electrical systems. So starting with the electrical domain, the electrical part of the motor, we have this armature circuit, and think back to how we might model a circuit such as this. We can in essence apply Kirchhoff's voltage law or Kirchhoff's loop law. And this is the result. And where this came from, if you think back, we start at one point in the circuit. As we go around the circuit, we pass through the voltage source. That causes an increase in the voltage. We have a bump in voltage across that voltage source, E sub A. And then as we go across the resistor, we drop voltage according to Ohm's law. So we drop voltage according to the product of the resistance and the current through the resistor. Then we drop voltage across the inductor, where the voltage drop is proportional to the rate at which the current is changing. Then we drop across the rotor due to the back EMF, at which point we're back where we started. And so, since voltage is a potential difference, the voltage around a circuit, the difference in voltage between a point and the same point, is 0. So that brings us there. We can also model the mechanical domain of the motor, the mechanical aspects of the motor. So again, thinking back to earlier lectures, think about how we might model the mechanical aspects of the motor. In essence, we can apply Newton's laws or Euler's laws. So we have this single inertia. We can draw a free body diagram and then write the equation of motion as sum of the moments equals J alpha. So in this case, if we look at this inertia, the torques or moments acting on the inertia are the torque generated by the motor, T, and then there's a resistance torque due to the friction. And so we model that friction in this manner. And in this case, we're modeling the friction as viscous friction, where the friction is proportional to the speed of the motor, or the speed at which the rotor is rotating. So these are the sum of the moments, and it equals J alpha, where angular acceleration is theta double dot, and J is the rotational inertia of the rotor. These two equations are then coupled by the previous relationships we had on the previous slide. So this is a completely electrical equation, but if you think back to back EMF depends on the mechanical speed of the rotor. So the electrical domain is coupled to the mechanical domain through the back EMF. Similarly, this is a mechanical equation, but the mechanical torque that's applied to the rotor is a function of the electrical current. where the motor torque is equal to the motor torque constant times the current through the armature. In this class, when we have to model electromechanical systems, I will expect you to be able to generate the equations for the electrical domain and the mechanical domain using the approaches we've learned previously. However, the sort of electromagnetic induction relationships I will give you. So for example, the relationship for back EMF, or the relationship for motor torque, I will provide you. Similarly, if I gave you a speaker or a solenoid or a sensor or something like that to model, I would again give you these coupling relationships, these electromagnetic inductive relationships. So let's go ahead and try and find a transfer function for our motor. So those previous equations give us one dynamic mathematical model of the DC motor. An alternative type of model is the transfer function. And in this case, I want to find the transfer function where the voltage applied to the armature is the input and the position of the motor is the output. You could imagine different situations where the inputs and the outputs might be different. So there could be a different situation where we want to consider the speed of the motor, and so that would be our output, or the torque of the motor, where that would be our output. So think back to how we find a transfer function. In general, we start with the differential equation model. So in this case, we have two differential equations, one for the electrical system from the previous slide was the applied armature voltage, subtract the drop across the resistor, subtract the drop across the inductor, and then we had the back EMF, E sub B, and I'll go ahead and substitute in that coupling relationship where back EMF is some constant multiplying the angular speed theta dot of the rotor. And that all sums to 0. Then we also had a differential equation for the mechanical aspect of the DC motor, where we had an external torque T, which if I use our coupling relationships, the torque is equal to the motor torque constant times the current through the armature. And then we had the frictional torque opposing the motion of the rotor, and it's equal to J alpha, where angular acceleration is theta double dot. So when we find a transfer function, we begin with the differential equations. We make a decision about what's the input and what's the output. That was given. That's our input. That's our output. And think about what the second step of the process is. The next step is to take the Laplace transform of the differential equation, assuming 0 initial conditions. So if we take the electrical equation, take its Laplace transform, E sub A is just some function of time. We take its Laplace transform, we get a function of S. R sub A is a constant, so it can just come out front. The armature current, again, is a function of time, so we take its Laplace transform, we get a function of S. The inductance is a constant, comes out front. If we take the Laplace transform of a derivative, differentiation in the time domain becomes multiplication by S in the Laplace domain. And then similarly, KB is a constant, and we have the derivative of theta, so differentiation again becomes multiplication by S, and that's all equal to 0. So we'll call this equation number 1. Then we do the same thing for the mechanical equation. K is a constant. The Laplace transform of I sub A is the Laplace transform version I sub A of S. The viscous friction parameter is a constant. The Laplace transform of theta dot, we get S because of the differentiation. And then on the right hand side, J is a constant, and theta double dot, since it's the second derivative, we'll have S squared, 1S for each derivative. We'll call this equation number 2. So this was the second step of the process, taking the Laplace transform, assuming zero initial conditions. The final step is to do algebra to rearrange this all into the form output over input, theta of S divided by EA of S. Looking at this, our input is EA of S. Our output is theta of S. And so if we look at these two equations, we have our input scattered around, we have our output, but we also have IA of S. We also have the current, which is neither our input nor our output. And so we need to eliminate this. Because it's neither our input nor our output. So if we look at this, think about how we might be able to eliminate IA of S between these two equations. In essence, we can solve one of the equations for IA of S and then substitute that expression into the other equation. So for example, from equation 2, we can solve for IA of S. So I can take this term, I can add it to the right hand side and factor out theta of S. So I had the JS squared already over there. I add the BS to the right hand side. I factor out the theta of S. And then I divide through by K. So that gives me an expression for IA of S, which I can then substitute into the other equation, equation 1. So these two terms have an IA of S. I can factor that out and sub this in. Going to the next slide, I'll complete the work. So looking at equation 1, I had EA of S. I then had the two terms with the IA of S. So I can factor IA away from the RA and away from the SLA. And then I substitute in for I sub A. I had JS squared plus BS divided by K times theta of S. Then I had the back EMF KB times S times theta of S. And that's all equal to 0. So now I have a single equation only in terms of our inputs and our outputs. IA has been eliminated. And then I just want to rearrange this into output over input. So in order to do that, I'll go ahead and keep the EA of S on the left hand side, and I'll move these terms with theta of S to the right hand side. So this negative, I'll add it over, it'll become positive. This negative, I'll add it over, it'll become positive. So I'll have the quantity R sub A plus S times LA. JS squared plus BS. I'll go ahead and factor out one of those S's. So I factor out one s, the s squared becomes s, I factor out that s. I also add this term to the right hand side. That becomes positive kb times s. And I factor theta of s away from the whole thing. Then one more step to rearrange it into the form output over input. The output is theta of s, the input is EA of s. So if I divide EA of s to the right hand side, I'm left with a 1 on the left hand side. And then I take this whole quantity and I divide it to the other side. So I have the quantity RA plus SLA times the quantity JS plus B. I have S divided by K, multiplying that whole thing. And I have KBS. If I take just one little simple step just to clear out these fractions, I like to have a transfer function that's just a polynomial divided by a polynomial. So if I multiply through by K on the top and K on the bottom, it's as if I'm multiplying by 1, so I'm not changing anything. And I get a transfer function K divided by S, which I can factor out. This first term has an S, and this second term also has an S, so I'll factor S all the way out of the denominator. Then I have this term due to the electrical dynamics in essence. I have this term due to the mechanical dynamics. When I multiply through by K, I'll cancel the K on that term, but then when I distribute, I'll also end up with a K on that term. And that gives us our transfer function. Again, transfer functions always have units, so let's presume that the units for position are radians and the units for the armature voltage are volts. And this gives us our transfer function, which is a dynamic model of our DC motor, our armature controlled DC motor. As I had mentioned previously, we may wish to create a transfer function for a different input or a different output. So very quickly, just by looking at this transfer function for an input of voltage and an output of position, can we think about what the transfer function would be if our output was speed? So let's call speed, or angular speed, omega. It's the derivative of angular position. So thinking about that, what might the transfer function with an output of speed look like? So taking the Laplace transform of this, we get omega of s. Here we have a first derivative, which becomes multiplication by s. And so we can see that omega is just s times theta of s. Since we have this common, we have this s in the denominator here, we can multiply through and bring it to the right hand side or the left hand side to get s times theta of s, which is equal to omega of s. So this transfer function will be exactly the same except without the s in the denominator. And the units will be different. Our speed will be radians per second, and our input will still be volts. Continuing on, let's try and look at a different model of a DC motor, or look at a DC motor from a different viewpoint. Let's try and generate a static model of the DC motor, or a model of the DC motor when it's in steady state. So thinking back to the previous slides, we found that the differential equation describing the electrical dynamics of the motor had this form. And so think about how this might change once we're in steady state. So you can imagine that the motor is just sitting there, we apply a voltage to it, the current through the motor changes, the speed of the motor changes, and eventually it reaches some steady state speed. So once it reaches that steady state speed, how does this equation change? Well, basically, since the current isn't changing anymore, the current through the circuit is constant, its time derivative is 0. And so this differential equation becomes the following. The relationship for motor torque is still equal to the motor torque constant times the armature current. If we solve for the armature current, we get that it's equal to T divided by K. And if we take that expression and substitute it into the first equation, we get the following. And this equation gives us a relationship between motor speed and motor torque in steady state. Let's go ahead and rearrange it to solve for T. So I'm going to go ahead and take this negative term with the torque in it, add it to the right hand side. Then to solve for T, I'll multiply through by K, and I'll divide through by R sub A. And if I do that, I get the following. So I move that to the right hand side, multiply through by K to cancel that, I get a K there and a K there. Divide through by RA to cancel that, I get a division by RA, a division by RA. If you look at this, you can see that the torque is a linear function of the motor speed. This is a constant. The motor torque, the back EMF constant, and the armature resistance are all constants. And then for a given applied voltage, this is also a constant. So it sort of has the form y equals mx plus b, where the torque is the dependent variable and the speed is the independent variable. And so we get a straight line relationship between torque and speed. Looking at this, the constant multiplying the independent variable is our slope. And it's constant and it's always negative because these parameters are positive and there's a negative sign in front. So we get this constant slope that slopes downwards, and this is a function of these parameters. And we also get that the intercept, the y-intercept, changes as we change the voltage applied to the motor. So you can see when we have one armature voltage, we get this line. We apply a different armature voltage, we get a different y-intercept. And so this is an alternative sort of model of a DC motor. Such a thing, a torque speed curve like this, can be used for sizing a motor. It can even be used for control in some instances, but you lose some elements of the motor's behavior, its transient response. But in some instances, this may be sufficient. In practice, the maximum torque of a motor is usually limited. And the reason that that is done is because at high torques you have high currents, and that can damage the motor if you do it for a sustained amount of time. In many cases, you may allow the motor to momentarily have a very high torque, but usually the control system will limit it so that it's not for a sustained amount of time, because that will cause damage to the motor. Here's another modeling example with a DC motor. So here we have a DC motor with an armature circuit and rotor inertia J sub 1 and friction B sub m. And the output of the motor is connected to another inertia, a load inertia J sub 2, via a flexible shaft with stiffness K and damping B. And we want to write the equations of motion. So this one will provide a good refresher on the modeling of mechanical systems. Before we begin, let's just take a second and think about how many equations of motion we need to completely model the dynamics of this system. It turns out we're going to need 3 equations. One equation for the electrical circuit and one each for the 2 rotational inertias. Starting off, we'll generate the equation of motion for the electrical part of the system, the circuit. So we have a voltage source, E sub A, then the rotor or armature has some resistance, some inductance, and then some back EMF. And so again, recall that we can model this using Kirchhoff's voltage law, Kirchhoff's loop law, where we will assume that the armature current flows clockwise. So starting at this point of the circuit, moving in the direction that the armature current is flowing, we'll initially have a bump in voltage due to the voltage source. Then we'll have a drop across the resistor, where the drop is equal to the product of the current and the resistance according to Ohm's law. Then we'll have the drop across the inductor, where the voltage across the inductor is proportional to the time rate of change of the current. And then we'll have the drop due to the back EMF, because the polarity of the back EMF opposes the polarity of the supply voltage. At that point, we're back to where we started, and so the total change in voltage around the loop is 0. If I just go ahead and quickly rewrite this and substitute for back EMF, where I know that the back EMF is equal to the back EMF constant times the rotational speed of the rotor. This gives us the first of the 3 differential equations that we need to describe the motion of this system. Moving to the next slide, we'll now go ahead and generate the equations of motion for the mechanical portion of this system. And so in this case, we have the inertia of the motor, the rotor, and it's connected via a rotational spring and a rotational damper to the other inertia, J sub 2. We've defined, if you look at the previous slide, the direction of positive angular motion. So theta sub 2 is positive in that direction, where theta sub 2 is the motion of J sub 2, and theta sub 1 is the motion of the inertia of the rotor, where it's positive in the same direction. And then we also make the presumption that the motor has some friction, where the viscous friction coefficient is given as B sub m. So in order to model this system, we can draw the free body diagram for each of the 2 inertias. We'll have inertia 1, J sub 1, where theta sub 1 is positive in that direction. The torque that's generated by the motor, that's applied to the rotor we'll presume is positive in the direction of positive theta 1. The frictional torque is going to oppose the rotation of the motor. So we can imagine some frictional torque, and we will model it as being proportional to the speed. The torque itself is proportional to the armature current. In addition to the motor torque T and the frictional torque, we will also have torques applied to the inertia due to the spring and the damper. And so again, this is a good review. And so the way that I usually determine the orientation of the spring torque is that I hold the second mass or inertia still, and I move the first inertia in the direction of positive motion. So if I move this inertia in the direction of positive theta 1, I will twist the spring, and the spring will want to spring back. So I can imagine that I'll have a TS in that direction. And the magnitude of the torque is proportional to the deformation of the spring. So it has some stiffness K, some spring constant K, and the amount of twist is equal to how much the one end moves minus how much the other end moves. Similarly, we'll also have a torque due to the damper, the damping in the shaft, except here the torque is proportional to the relative speeds, the difference in the relative speeds of the two ends of the damper. So this is the free body diagram for J sub 1. We can also draw a free body diagram for J sub 2, where theta 2 is positive in the same direction as theta 1 is positive. And I can do the same sort of process where I could hold J1 still, move J2 in the direction of positive theta 2, imagine the spring twisting and then wanting to spring back. The alternative to that is to just draw the torques as being equal and opposite to the torques applied to the other inertia. So you can imagine that if you took this spring and you twisted it, the torque generated on the two ends would be equal and opposite. So you could imagine that T sub S and T sub D are equal and opposite the application on J sub 1. And this direction, as I've defined it, presumes that T sub S is defined in this manner, where the ordering is theta 1 minus theta 2. If I switch the order of theta 2 and theta 1, then the torques would be positive in the opposite direction. Once we've drawn the free body diagrams, we can then go ahead and generate the equations of motion. So we'll do it first for inertia 1, and we will apply Newton's laws or Euler's laws, where we have that the sum of the moments is equal to J alpha. So in this case, we have torque T in the direction of positive theta 1, so it is also positive. We have the frictional torque in the opposite direction, and then we also have the spring torque and the damper torque in the opposite direction. And it's equal to J times angular acceleration, where the rotational inertia in this case is J sub 1, and the angular acceleration is theta 1 double dot. then we can substitute in the different expressions we have for the different torques. So we have the motor torque is equal to the motor torque constant times the armature current. Subtract the frictional torque, where we're actually given that the viscous frictional coefficient is B sub m. B sub m, theta 1 dot. Then we have the torque due to the spring, which is K, times theta 1 minus theta 2, minus the torque due to the damper, which is B, times theta 1 dot, minus theta 2 dot, and that's equal to J1 theta 1 double dot. So this is our second differential equation for the equation of motion. And then finally, we have the equation of motion for the second inertia, where again it's sum of the moments equals J alpha. In this case, the only two torques that we have acting on the inertia are the spring torque and the damper torque. They're both pointing in the direction of positive theta 2, so they're both positive. The inertia in this case is J sub 2, and the angular acceleration for this inertia is theta sub 2 double dot. Substituting in expressions for T sub s, we have K times the quantity theta 1 minus theta 2. Substituting for T sub d, we have B times the quantity theta 1 dot minus theta 2 dot, and that's all equal to J2 times theta 2 double dot. And so this gives us our final and third differential equation needed for modeling this system. If you think back, one quick and dirty way for us to give some confidence that we've oriented our torques in the right direction is to look at the signs on our variables. So in these sorts of systems, all of the theta 1 terms should have the same sign, and all of the theta 2 terms should have the same sign. So here, if I distribute this negative k, this becomes positive. If I distribute this negative b, this becomes positive. So all the theta 2 terms in this equation are positive. If I add all of these negative theta 1 terms, negative, 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 to the right-hand side, then the theta 1 double dot, the theta 1 dot, and the theta 1 terms are all positive. And so we have the same signs, and this is a good check. Same thing with equation number 3. K theta 1 is positive, B theta 1 dot is positive. If I add negative K theta 2 to the right hand side and negative B theta 2 dot to the right hand side, then all the theta 2 terms are positive. This basically concludes our discussion of the DC motor. And we'll just summarize a few limitations of this implementation of a DC motor. One is that there's quite a bit of friction and wear between the brushes and the commutator. You can imagine these brushes constantly rubbing against the commutator. This creates friction, which hurts the efficiency of the motor, and it can also wear out. You eat away, you wear out the brushes, you lose a connection, and the motors don't work. So the sort of robustness of a DC or brush DC motor can be limited. Another issue is the fact that you have this current flowing through this long winding of resistive material. This wire generates heat, and since that heat is trapped in the center of the motor, it's difficult for it to escape, and this can cause problems with the motor being damaged. This was one of the things I had said previously about not wanting to run the motor at its peak torque for a very long amount of time, because that current that is needed generates heat, which can damage the motor, melt the windings, etc. DC motors can sometimes have limited speed range and limited efficiency, and some of these issues can be addressed with an AC motor. And so subsequently we're going to discuss a few different types of AC motors more at a conceptual level, just the basis of their operation, without getting too much into the mathematical details. One type of AC motor that's important for electric vehicles is the permanent magnet synchronous motor, or the PM synchronous machine. It's a type of AC motor in the sense that the current through the motor alternates direction. The current alternates, that's what AC stands for, alternating current, as opposed to the DC motor where the current remains in the same direction, direct current. A PM machine is also sometimes called a brushless DC motor. The fact that the frequency of the alternating current must change, that means that the source must be from a DC supply. So it's sometimes called a brushless DC motor because the supply is DC, even though the current itself is changing direction. And the way that the DC supply is changed into alternating current is through the use of an inverter, either to create a sinusoidal or approximate a sinusoidal current, or what we call trapezoidal current. I've seen in some instances that machines where the current is trapezoidal is called a brushless DC, and a machine where the current is sinusoidal is called a synchronous AC machine. Another reason why a PM synchronous machine is called a brushless DC motor is because the speed-torque characteristics of the motor are similar to a brushed DC motor. As I'll show subsequently, the mathematical models for the two types of motor have the same sort of structure. Here's a picture of this type of AC motor, which we can use to better understand how it operates. So the rotor itself is a permanent magnet, and the stator consists of three phases of windings: an A phase, a B phase, and a C phase. The current in each of these phases is approximately sinusoidal or trapezoidal. It's alternating current, and that alternating current is approximated from a DC source, from a battery, using an inverter like this. And so by changing the frequency and the order in which these switches are opened and closed, we can approximate alternating current in each of the three phases, which you can see here. So it may not be perfectly sinusoidal, but we can sort of approximate it with small steps. Thinking back to that previous picture, the rotor is a permanent magnet, so the magnetic field is fixed, and this is where part of the name comes from. That's why it's called a permanent magnet machine. And the coils on the stator are energized in sync with the rotor. So that's why it's called a synchronous machine. So looking back on the previous slide, the current through each of these three phases, they're at their peaks at different times. And by doing that, the magnetic field generated by each of the phases moves, interacting with the permanent magnet rotor to sort of pull or push it around the motor. In order to synchronize the energizing of the different coils, we need to be able to sense the motion of the rotor, and that can be accomplished in a number of ways, some of which we've discussed previously, including Hall effect sensors, optical encoders, and maybe most commonly resolvers. And the control of the synchronization is very important to the operation of the motor. This is something we'll talk about a little bit later on in the course. And the fact that there are no brushes, the armature itself is in the stator and it's stationary, so we don't have any need for brushes in order to get electricity to the stator. So there's less worry with the brushes wearing out. And the fact that the armature is on the external part of the motor means that it's easier for heat to escape. And so this solves a couple of the issues we saw with brushed DC motors. That's not to say that PM synchronous machines don't have their own drawbacks. They can be more expensive. They can have issues with safety, in that the magnets in the rotor can come loose or become demagnetized if the motor gets too hot. And this type of motor can also sometimes have a limited constant power range. So here again is a picture of this type of motor. The stator field is generated by these three-phase alternating current. And even though in this picture the phases are sort of concentrated in these three locations, in general the windings are distributed around the outside of the motor in order to get better torque properties and reduce cogging. But again, the windings may be distributed either sinusoidally or trapezoidally. When we model an AC machine like this, a three-phase machine like this, we can model each of the circuits individually. So just like with a DC motor, how we had an armature with some lumped resistance and some lumped inductance and a back EMF and all that, we can do the same thing for each of these three phases. Alternatively, we can represent the three phases all together, all at once, as a single rotating current space vector. And this won't be entirely clear from this picture, but there's an animation on the next slide. The current through each phase is changing sinusoidally, so getting larger and smaller, becoming negative and then positive. So each of these three phases are alternating at different times. If we sum all three of the phases, all three of the sinusoidal currents, we get a vector whose amplitude is constant, but whose direction is changing as the three phases are energized in succession. And then the control is to maintain the current space vector in a certain location relative to the magnetic field. And thinking back to a cross product, where force is the cross product of current with magnetic field, the force will be greatest when these two vectors are 90 degrees apart. So the control, in order to achieve maximum torque, will keep the space vector I sub s 90 degrees ahead of the rotor, which is generating the magnetic field. Okay. So here's an animation that's sort of showing this concept of a space vector. Here's the A phase, and it's alternating. The current through this phase is alternating sinusoidally. So it's negative, and then it's 0, and then it's positive, and then it's back to 0. So the phase through this current is alternating sinusoidally. Same thing with the B axis and the C axis. And so when you sum those three together, you get this black vector, which is the space vector I sub s, which has a constant magnitude, but its phase or its direction is changing as these three phases are energized in succession. Here's a picture of a permanent magnet synchronous machine from the first generation hybrid escape. Here is the rotor, which is a permanent magnet rotor. These little squares are the magnets, and just like we saw previously with regular DC motors, we typically have more than just the two poles, more than just one north and one south pole, and that's what's being accomplished here. And here we have the stator, which has three phases. You can see the three connections to the windings representing each of the three phases, and you can also see how the windings are distributed around the outside of the stator, as opposed to being concentrated in three distinct locations. And then here's the larger system, where this large motor is sort of the traction motor for the vehicle, but then there's also a generator, which is also a permanent magnet, a synchronous machine, but is slightly smaller, and they're connected via a planetary gear set like we talked about earlier in this semester. So briefly, we want to compare the DC motor we spoke about earlier to this brushless DC motor, this permanent magnet synchronous machine. With a DC motor, the magnetic field has a constant direction because it's produced by a stationary magnet. So this magnet with its north pole and this magnet with its south pole are always located in the same direction, in the same location. They're stationary. So B is stationary. And then the current vector is made stationary by commutator action. If there wasn't a commutator, in essence the current would flip back and forth as the rotor turned. But through the use of the commutator, we always are able to keep the current basically pointing in the same direction. With a brushless DC motor, the magnetic field is generated by a permanent magnet rotor, which is spinning. So this magnetic field is moving, and this current space vector, I sub s, also moves, and it's kept in sync by using a control system. So in essence, the brushless DC motor achieves sort of electrical commutation, where the energizing of the three phases is done in order to try and keep the current space vector 90 degrees ahead of the magnetic field in order to generate the maximum amount of torque. So looking at these are very similar, and we'll show that a little bit further. So the previous example showed the similarity, and it turns out the mathematics are basically have the exact same structure. So the torque itself can be calculated in the same way, where the torque is proportional to the current in the armature, as long as the angle between the current space vector and the magnetic field are kept constant. So if that angle is kept constant, then the relationship between current and torque is also constant, and we have this proportionality constant K, which is the motor torque constant. And the armature in this motor, even though it's static, even though it's part of the stator, it still has the same dynamics in the sense that it still has resistance and inductance because it's a piece of wire that's wound, and it still has a back EMF. In this case, you have a back EMF because you have a conductor in a changing magnetic field due to the rotating rotor, whereas with a regular DC motor, the magnetic field was constant, but the conductor was moving. But in each case, you still generate a back EMF. And the rotor also has the same sort of mechanical dynamics in both motors, because in both cases the rotor has inertia and there's friction. So looking at this, the two types of motors have the exact same mathematical form. This is one of the reasons why a permanent magnet synchronous machine is sometimes called a brushless DC motor. What's different, however, is that sometimes the relative values of the parameters may be different. So here are the dynamic equations representing the permanent magnet synchronous motor, exactly the same as a brushed DC motor. In this case, I sub s is the current space vector. One way in which the parameters tend to be different between the two motors is that with a brushed DC motor, the inductance tends to be relatively small, but with a PM synchronous motor, the resistance tends to be smaller. With a permanent synchronous motor, the friction can also be smaller than with a brushed DC motor. Another type of AC machine is called an induction motor. An induction motor has a similar stator where the armature is stationary on the outside of the motor, three-phase, but the rotor itself is different. So in a PM synchronous machine, the rotor is a permanent magnet, but in an induction motor, the rotor has this sort of form, sometimes called a squirrel cage. And so it's not a magnet, and there's no physical electrical connection to the rotor, but current is induced in the rotor by this conductor being in the presence of a changing magnetic field. And so this current is induced in this squirrel cage, which creates a magnetic field which interacts with the magnetic field from the stator, causing a force which moves the rotor. And in the same way that we were able to analyze permanent synchronous motors, we can either model this on a per phase basis. This is a three-phase motor, so you could have a circuit for each phase with a stator part, the induction of the current into the rotor. So this could be one phase in an induction machine. Or we can model it using the equivalent current space vector I sub s, where we sum the currents through each of the three phases, phase A, phase B, and phase C. So this brings us to the conclusion of Module 9, where we discussed electromechanical actuators. We first described how solenoids worked, then we discussed DC motors in quite a bit of detail, generating both dynamic models and static models of a DC motor. And then we discussed a couple of important AC machines, the permanent magnet synchronous motor and the induction motor. At more of a conceptual level, we didn't quite get into the same amount of detail. But if you take another course in electrical machines proper, you'll get into the AC machines in much more detail.